welcome to our session today. My name is Temba. Today we're exploring current, in the context of electric circuits, in the broader knowledge area of electricity and magnetism. But we'll zoom our attention into understanding, the concept of current, right? Remember, we by now most probably familiar with the fact that there is, energy involved in as far as the circuit is concerned. We think of the battery as the primary source of energy. So the transformation of energy takes place throughout the circuit. So our discussion on, the bolts and nuts or the detail around the idea of current will be in the context of an electric circuit, right? So let's look at the overview in terms of where we are. Okay, so what do we know? We know that the battery is the primary source of energy, okay? So the battery provides energy for every coulomb of charge in terms of moving, charges in the external circuit. We also know that EMF is actually the maximum energy that a battery can supply, for every coulomb of charge. Now, in as far as, current is concerned, we know that current is transmitted through materials which we would describe as conductors. So what are conductors? These are metallic, materials that allow charge to move through them. And then insulators will actually do the opposite of conductors. These are the type of materials that do not allow electric charge to move through them. So insulators are essentially, bad conductors, while conductors are materials that allow charge to pass through, right? So the concept of current will be discussed in electric circuits, right? Now, the thinking that is going to guide our session for today are the following. Okay, have you ever thought about, number one, why is an ammeter always connected in series? We'll talk about an ammeter as a device that is actually used to measure current in a circuit. And then the second thought that you must think about it, okay, just to guide, our understanding, is that what does the ammeter reading tell us about how much charge moves in a circuit? So the ammeter is actually is the device that measures current, and then the reading that we get from the ammeter, what more does it tell us in our understanding of what current is all about, right? Okay, now the keywords, the terminology, very, very important. One has to emphasize at this point that whenever we talk of definitions, our point of reference becomes the examination guidelines. Keywords must be used in the correct context, and furthermore, we are saying that the definitions, which forms part of the language, is actually an all or nothing kind of an arrangement. It's either you know your definitions or you don't. But beyond reciting and memorizing the definitions, we also need to understand. So our lesson focuses on the understanding. That's why we emphasize on the thinking, how you must think as a young scientist, right? So current is the main concept for today, which is a quantity, okay? Remember, a quantity is anything that can be measured, because in the context of current, we'll talk about moving charge, either positive or negative. Think about the subatomic particles, okay? So when you talk about charge, think about the subatomic particles, all right? Okay. Now the subatomic particles are actually your protons, electrons, and neutrons. And then when we talk about current, we're talking about the electrons, okay? And then the word rate is used in many scientific contexts, as you discover as we move along. When we talk about rate, it has a component of time. So when we talk about the rate of something, let's say for argument's sake, rate of moving charge, we are asking ourselves how much charge moves past a point in a given time. So the unit of time, again, very, very important, is a second. So if we talk about a unit, we're talking about one. Okay, so if we talk about a unit of time, what are we referring to? We are referring to 1 second. Okay, so the rate has a lot to do with time or time interval, okay? The change in time, all right? Okay, and then by now, we most probably familiar with the key components of a simple electric circuit from our earlier grades. We understand that for us to set up a simple circuit, we need certain instruments or certain components that make up that electric circuit. But the main idea behind a circuit is just to say to us that, look, energy is transformed from one form to another, as we know it from our background that energy cannot be created or destroyed. So it means that there must be, some form of energy converted or transformed to the other. So a circuit, as an example, says to us that energy is actually converted from one form to the other. So in constructing a circuit, we need a certain, components. What are these components? We need a cell. By now, we know that a cell is just a single unit with a pair of terminals, positive and negative, which is obviously going to be connected to a conductor, okay? And then a battery becomes a combination of cells that are connected in series, 2 or more. Then we have got a battery. So a cell or a battery becomes the primary source of electrical energy, okay? A conductor, we've spoken about it briefly to say that what a conductor does, it's a material in terms of physical properties that allows charge to pass through. So if we talk about electrical conductivity, we're talking about materials that allow electric charge to pass through them, as opposed to thermal conductivity, which has a lot to do with heat under physical properties of materials. So materials that allow charge to actually pass through them justifies even their use in everyday life. You think of copper wire, a nichrome wire, stainless steel. Most of them are used as electrical conductors in, circuits in our homes, because circuits, they just are not confined to, the small circuits that we construct in our school labs, but even beyond, outside the classroom, there are a lot of practical applications of electric circuit, which is the big idea of why we have to understand the science behind it, right? And then we also have a light bulb, okay, that represents a single light bulb, which also is connected to a conductor in a typical circuit. And then we've got a closed switch, okay? Okay, in a closed switch, actually, it says to us that current will be flowing, and then this is a broken switch or an open switch. So if a switch is open, it means the circuit is broken. It means there is no current in the circuit. All right. Now, let's go to our simulation just to show how exactly we set up an electric circuit. Right. Okay. Okay. Actually, it is. Okay, did you pause? I must take it from the top. Okay. Okay. How much time are we having there? 8. Okay, we're still good. Whenever you're ready. Once again, let's look at this, how exactly we set up a simple electric circuit. What do we need for an electric circuit? We need an energy source, in this case, which is a battery, okay? Now, this is a cell in a way. Why are we saying it's a cell? Because there's only one unit, okay? But if we have got multiple of them connected like that, it becomes a battery. So for a change, let's talk about a battery, okay? This is a source of electrical energy, okay? Now, we've got conducting wires, okay? These are materials that allow electric charge to pass through them, okay? We will connect another one in the opposite terminal of the battery, right? And then we can have our switch. We will use the switch to complete or break the circuit, depending on whatever we need to achieve, right? Okay, we still have our conducting wires, which most probably it looks like a copper wire, okay? And then we can have another one, okay? And then we can also have a light bulb, okay, just to show the energy transformation that takes place, okay? There is our light bulb, and then we will complete the circuit by connecting another piece of conductor. So that's our circuit. As it is now, the circuit is broken. What does it mean? The charges are there in the conducting materials, but these charges are not moving. Why? Because charge can only move once the circuit is complete. Okay, as it stands, the circuit is broken because the switch is open. But the moment we close the switch, okay, this is what is happening. Charges are moving. The battery provides energy or transfers energy to each and every charge such that they move through the circuit. But when these charges, which have got electrical energy, reach the light bulb, what is happening? There is some energy conversion. That electrical energy is actually converted to light. As you can see, the bulb is glowing. Okay, so if we break that circuit, you know, the light energy ceases to exist because that energy can only be there once there is electrical energy, which is transformed by the light bulb into light energy. So this is how we set up a simple circuit, right? So all these components that we have listed, your battery, your switch, your conducting wires, your light bulb, are the basic components that you need to set up a simple electric circuit, right? Okay. Now, so these are the symbolic representations of the different components that we might have. So in this case of the, you know, the simulation that we just showed, we have got a battery instead of a cell because we had a combination of, you know, two cells connected in series. Okay, we'll talk about that more as we go along, right? And then the new thing here is an ammeter. Okay, the new component that we have introduced is the ammeter, which is used to measure current. Okay, so an ammeter, this is how we represent an ammeter in a circuit. We'll connect the ammeter, obviously, at a point in a circuit just to determine how much current passes through. So the measurement of current is done by the use of an ammeter, right? Okay. Now, let's talk about electric current, which is our main concept for today. Electric current is defined as the rate of flow of charge. Okay, the word rate has come up. Okay, that's our first encounter with it. When we talk about rate, we are saying how much charge passes through a point in a given time. So if we talk about a rate, we are saying, let's say for argument's sake, we talk about 5 coulombs of charge passing through a point per second. So the rate is 5 per second. That's the idea of the term rate. So the definition of current is incomplete without the keyword rate, right? So the symbol for current is I, okay, which is derived from current intensity, which is an indication of what is the intensity of charges flowing through a point per unit time. So the SI unit is the ampere, which is the capital letter A, okay? Right, and then by mathematical representation, we know that current is amount of charge that passes through a point in a given time. Then it takes us to the mathematical equation, I is equals to Q over delta T, where Q represents charge, okay? This charge is obviously electrons, okay? We know from conservation of charge. So then charge is measured in coulombs, right? While time is measured in second. This is the time interval, okay, through which a certain amount of charge passes through a point. So time is in seconds. Then the SI unit, by definition, when do we have an ampere of current? These are important questions in terms of understanding that we need to ask ourselves. When do we have an ampere of current? Understanding that current is rate of flow of charge, or how much charge passes through a point per second. So if we talk about an ampere of current, we are saying that there is 1 coulomb of charge passing through a point for every second, right? So if we talk it in terms of electrons, we know from quantization of charge that charge is equals to the number of electrons multiplied by the elementary charge. So if we have got a coulomb of charge, how many electrons must pass through a point per second? Now we can determine the number of electrons that must pass through a point, which is Q, in this case it's 1 coulomb divided by the elementary charge, which is 1,6 times 10 exponent negative 19. Here we want the number of electrons, okay, as per the principle of quantization of charge. Let's check how many electrons make up a charge of 1 coulomb so that we better understand this. Right, so in this case, we've got 1, okay, divided by, what do we have? 1,6, okay, times 10 exponent negative 19, okay? What do we get from that? We get 6,25 times 10 exponent 18, okay? This is 6,25 times 10 exponent 18 electrons, right? So in other words, what do we mean? We are saying that for us to have an ampere of current, there must be that number of electrons passing through a point in a conductor in 1 second. Okay, so we're trying to link what we already know to, the new knowledge. Now, having said that, let's understand that current is the rate of flow of charge. If we break it down to make it simpler, we are saying, let's ask ourselves, if we have a reading of current, what exactly are we talking about? If it's an ampere of current, it means there is 1 coulomb of charge passing through a point for every second. Equivalently, if we have got 10 amperes, it means there's 10 coulombs of charge passing through a point in a conductor for every second. After a short break, we'll talk about how exactly we measure current in practice using our device, which is the ammeter. Let's take a short breather for now. Welcome back to our second segment. We're still exploring current. Now we want to shift gears and look into exactly how do we measure current in as far as, a simple electric circuit is concerned. Because, the current reading must be an indication of how much charge passes through a point per unit time. So that's the kind of thinking that we must have. But also, forget not the big questions that we asked. Why do we exactly connect the ammeter in series or at a point? What's the justification? There is some scientific thinking around it as long as we understand the concept of current. Right, now measuring current in a simple electric circuit. Okay, we have already indicated that an ammeter whose symbol is that, okay, it's an A inside a circle, so that represents an ammeter connected at a point, okay, is a device that is used to measure current or strength of current. Okay, so take note, we talk of current in terms of charge per unit time, or we can talk of strength of current in terms of how much charge, the greater the amount of charge passing through, the stronger the current. Sometimes we may also alternatively refer to it intensity of current. So current, strength of current, current intensity, it may be used differently to refer to this quantity of current. It refers to the same thing, right? So the older version of the device, this is an analog one, which is an ammeter in real life. It looks like this. So it has got 2 calibrations, okay? So when you connect it obviously at a point, okay? The black one represents the terminal where you place the positive terminal, while the red is the negative. And then you'd also realize that there are 2 calibrations or graduations. The other one ends with 1, the other one ends with 5. So when you connect to a circuit whose current you do not know, you obviously start with the bigger one, okay? The moment the current reading, that pointer deflects very, to a slighter extent, it says the amount of current that you are measuring is very little, it's below 1, then you can change it and put on the middle one, okay? So this is just how an older version of an ammeter looks like in real life. But due to advancement in technology, because we are living, in the 4th industrial revolution now, we are having this version of a multimeter, which is digital. So this is digital, even in terms of, accuracy. This is more common nowadays. It actually gives you the reading electronically, so you don't have to, do the check between those calibrations and obviously widen the margin of error, okay? So that's our digital multimeter, right? But now let's look at measuring current in a simple circuit. Let's go back to our simulation and look at a simple circuit, right? Now, what do we need in a simple circuit? Let's take just one battery, one cell, okay? and then we connecting wires, the conductors to it, okay? And then we can have also our switch so that we can break and complete the circuit whichever way we want it, okay? And then again, we can have a light bulb just to show us how much current passes through that battery as well as through the external circuit. So I'll have the light bulb there, okay? And then the connecting wires. And then we have our ammeter here. I'll take a digital one, like the one that we showed on the slide. Okay, that's our ammeter there, okay? That will connect to our circuit, okay? And then complete that circuit, okay? Right. So a simulation actually models what happens in real life, you know. It also helps us to understand, as it stands, there is zero current, there is no current in the circuit. Why? Because the circuit is broken. We can even show the charge, okay? The charge is not moving. So once there is no flow of charge, then there is zero current while the switch is open, okay? We'll take out those charges. What if then we kind of, let's have a smaller light bulb there, okay? Let's give it, say, 3 ohms of resistance, okay? Now, if we close the switch, okay, there is an ammeter reading there. So you'd realize that the ammeter is connected at a point, okay? Now, there is something very interesting here. There is only current in the circuit while the circuit is complete. That speaks to the energy, okay? Even if we show the charge, okay, can you see the charge is moving from, it is provided the energy from the source, which is the battery, throughout the conducting material. Those charges, as they start to move, there is electrical energy, which is converted to light energy by the bulb, okay? It passes through the ammeter with a reading of 3 amperes, okay? So we can take that out for now. So that's how we actually measure current in a circuit, right? Okay, if we can go back to our discussion, okay, let's talk about the ammeter as a device. So this ammeter in real life is actually a low resistance device that allows total current to pass through it. Now back to the simulation, let's add another ammeter again here and see how we want to discover something very important about current. We'll add another ammeter onto this circuit just to get a sense of exactly what happens when current flows through a circuit, right? Okay, we'll take that apart just to try and organize it, okay? There is our circuit, okay, right. We can also try and understand that, when current actually, when the circuit is connected, the current that flows through, a single pathway stays kind of the same, okay? So here is our circuit, okay? We've rearranged it and put 2 ammeters. Now, in both cases, there is 0 ammeter reading because there is no current. Why? The circuit is broken. But the moment we close, there is something very interesting. The first ammeter reads 3 amperes, while the other one reads 3 amperes. Now, in the point that we're trying to make, we are saying that the position or the connection of an ammeter in a circuit does not affect the total current in the circuit, which is why we say an ammeter is actually a low resistance device, right? Okay. Now, going back, it says the ammeter is connected in series. When we say we connect in series, we mean that it is connected at a point. The idea is to establish how much charge passes through that point per second, okay? So if we go back again, we would also understand that the 2 ends of the ammeter, because even if we represent it symbolically, we've got an ammeter, one end is connected to the positive, the other end is connected to the negative terminal, right? Okay, so we have managed to measure our current, but there's something again about current that I want us to kind of discover now, okay? Which is something that we already know, right? Now, what happens if the ammeter reading changes or whatever would have happened, I just want us to look at the, the brightness of the light bulb, okay? Now, we'll start with something that we know from our earlier grades. We'll start with a current of 1 ampere. Just check the brightness of the bulb when there is current of 1 ampere. By the way, what did we say is an ampere? It is when 1 coulomb of charge passes through every point per second. So there's that number, 6.28 times 10 exponent 18 electrons passing through a point for every second. As you can see, that's how current is flowing. Now, what if we increase the amount of current? We also want to check the brightness of the light bulb. Okay, let's increase that to say 3. Okay, we double the current. Okay, look at even the rate of flow. It means now these charges are moving even faster. As the charges move even faster, what happens to the brightness? Now, the bulb glows even brighter. So current strength is an indication of how much charge passes through a point. Now, from 1 ampere to 3 amperes, so it's 3 times as more amount of charge passing through that point per second. So the greater the amount of current, the greater the number of charges passing through a point per second. And when we talk about a second, we're talking about 1 second, which is a unit of time. Let's make it even more and see what happens. Let's make that, say, 12 volts. Okay, you can see even now it's 4 amperes. 4 amperes, even brighter. Okay, so now there is some relationship that exists here. The greater the magnitude of amperage or current reading, the more the quantity of charge passes through a point per second. And why do we continue to emphasize a point? Yes, we connect the ammeter in series or at a point because we want to know how many of those coulombs of charge actually pass through that point for every second. Right, let's go back to our simulation. Okay, so we can now relate the current to the intensity. So hence we spoke about strength of current, which says, okay, if we've got 3 amperes, this current strength is greater compared to that of an ampere, which is 1 ampere. We also saw even how fast the rate of flow. So it goes back to the definition, which says current is defined as the rate of flow of charge. So the greater the current, the greater the rate of flow. Hence, we would see even the brightness, meaning that even the amount of energy, transferred, per coulomb of charge is greater because we kept on changing, and then we also realized that the brighter the bulb glows. Okay, in the second segment, we'll look at the concept of current in terms of, the mathematical calculations and try to bring in some form of understanding to say, okay, how does amount of charge affect the current in a given amount of time? Okay, we'll take a short break for now. Welcome back to our final segment. Now we're looking at the concept of current in terms of, the mathematical equation. How exactly do we solve problems that relate to the concept of, current? But remember, the facts still remain that current is the rate of flow of charge. So we're asking ourselves important questions like, okay, think about what exactly it means when we've got a current of 3 amperes or when there is an ammeter reading of 3 amperes. Now that we have demonstrated how exactly we measure current using an ammeter by connecting it in series or at a point so that we get an indication of the amount of charge that passes through that point per second. So the main question here is, what exactly does the magnitude of the ammeter reading tell us about an electric circuit? And then secondly, what if there was double the amount of current registered by the ammeter? So now we've got 3 amperes, all right? And then if we double 3 amperes, what do we have? We've got 6 amperes. Now, what does that tell us about the current strength or the current intensity? Or alternatively, what does it tell us about how much charge passes through a point in 1 second? So if it's 3 amperes, we are saying that there's 3 coulombs of charge, whatever that number of electron is that pass through that point in a second per second. So if we double it to 6 amperes, what does it mean? It means there's 6 coulombs of charge passing through that point per second, right? And then what does the brightness, this is a very important observation that we made in the previous demonstration. What does the brightness of the light bulb suggest about current in a simple circuit? There's something that we realized, that the more current passes through a light bulb, the brighter that light bulb burns, okay? So in other words, it says to us, if there is more charges passing through that point per second, it means the brighter the light burns, because that has also to do with something very, very important, which is the energy conversion that takes place in a simple circuit. So these are some of the thinking points that you have to actually consider, just to guide us for the purpose of our discussion. Now we want to measure the current passing through a simple circuit where we connect a light bulb, okay? Now, if we go back to our simulation, we will get something of this sort, okay? Now, I'll break that circuit just for us to, to actually measure the current, okay? Now, if we close the switch, there will be current, okay? Or charges will flow. That's very important because we are saying charges flow, and the moment there is rate of flow of charge, there is current. So we don't use the term current flow, okay? We need to try by all means to stay away from that. Now, if we close the switch, the bulb burns. Now, you need to realize something here. The amount of charge that passes through the first ammeter is actually 4 coulombs of charge. Even after the battery, after the light bulb, they're still the same. So then the amount of charge actually remains the same, which takes us to something that we already know, which talks about the amount of charge remaining constant. Okay, what is that about? It has a lot to do with the principle of conservation of charge. Charge, in the amount of charge, as long as it's a closed system, it will remain constant. So as a result, charge is never lost, okay? Even the energy that is transferred by the battery to these charges remains constant, because we're still emphasizing that, in an electric circuit, there is a lot of energy conversion that takes place. We discussed that earlier to say chemical potential energy from the battery or the cell, whatever the case may be, is transferred to these charges. And then the moment these charges are given energy to move, which we talk about in terms of voltage, energy per coulomb of charge, then we've got electrical energy. What if now this electrical energy reaches the light bulb? What does the light bulb do? There's further energy transformation on the light bulb in terms of electrical energy to light energy. Okay, so the principle of conservation of charge says to us that the amount of charge remains constant. So even if we've got 4 coulombs of charge passing through the first ammeter, and then we also have the same amount of charge passing through the second ammeter. So is there any charges lost in this circuit? Definitely not. So the amount of charge remains constant, because we want to think of a circuit as a closed system of some sort, because we're already familiar with the principle of conservation of charge. So the amount of charge passing through second ammeter is equals to that which passes through the first ammeter. So in other words, we can also tell from this simple circuit that there's the same number of charges pass through the light bulb, which is also a very important realization that we have to arrive at, okay? Right, so that's how we measure current in a simple circuit across through a light bulb, okay? Now, the strength of current in a circuit is determined by the resistance of the circuit. Okay, the term resistance is starting to come up, we're starting to use it once too often than others. So the word resistance, we would understand it in the concept that it has to do with the other devices that are connected in the circuit outside the battery for now. So what are we saying? We are saying that a light bulb offers some resistance. If a light bulb has got, a certain amount of resistance to the flow of charge or to that current, then it has to do with the amount of energy that it converts from electrical to light energy, because that's what a resistor does, okay? So these are components in a circuit. An example is a light bulb. So we can say e.g. light bulb, okay? So a light bulb will convert electrical energy to light, heat and light. A speaker will convert, electrical energy to sound energy. So we're still maintaining that indeed energy cannot be created or destroyed. So energy is never lost by all means. Energy is transformed from one form to the other. So we can talk of a speaker as well as an example, a heater, But in real life, we talk of, television sets, your fridges, your microwave oven, heating and, devices that we use or appliances that we use at our homes. Okay. So the strength of current is determined by the resistance. This will lead us to even more, understanding as we go further in our study of circuits. Okay. Now, the battery stores a limited amount of energy, okay, for moving charges. So the battery does not release charge. Once again, what it does, it transfers that chemical potential energy to the charges so that the charges can move, so that it becomes electrical energy. We need to get that out of the way. So the charges are not from the battery. The battery is the primary source of energy, which is transferred to the charges, okay? Very, very important, okay? So a battery may be designed to deliver, let's say, a current of 1 ampere for 48 hours, right? So we are going back to the point that the amount of current will also be determined by the resistance of the components that are connected in a circuit. So say, for argument's sake, we've got a simple battery that delivers a current of 1 ampere for a period of 48 hours before we consider the battery to be flat. So the moment the battery is flat, what are we saying? In other words, we are saying that there is no more chemical potential energy to be transferred or to the charges so that they can be electrical energy. That's what it simply means. Now, if a circuit draws a stronger current, we already know something about current intensity. So 2 amperes is double 1 ampere. So it means if we connect it to an appliance that has got greater resistance, which draws a current of 2 amperes, that battery will only do the same job but for half the time, okay, before we consider it to be flat. So instead of it lasting for 48 hours, because it was designed to supply 1 ampere of current for 48 hours, so in half the time, the battery will be flat. Half the time is like, what, a day, which is equivalent to 24 hours, okay? So this has to do with the real life application of current, okay? Right. Now, the direction of current in a circuit, very, very important, okay? Electrons are the charges that, whenever we talk of charge in a circuit, we're talking of electrons by convention. We'll explain what that simply means, okay? So electrons are the ones that actually move through the circuit. We'll demonstrate that using a simulation once more, okay? Okay, this is what we have, okay? It's a closed circuit, okay? If the circuit is complete, let's show the charge is moving. There we go. So there is 4 amperes, meaning there is 4 coulombs of charge passing through every point for every second. So this is the direction of flow of what? Of electrons, okay? But we have got what is called the conventional current flow, which is what is standard. So we understand the flow of current with respect to conventional flow. Let's show the conventional flow. So the conventional flow is from positive to negative. This is what it is. So these arrows, they show the conventional flow of current. And in our discussion from now going forward, we always talk about current moving from positive terminal of the battery to the negative. Even through the ammeter, it will be from the positive to the negative terminal. So that's about the conventional flow of current. So each time we talk of conventional, we talk about the standard, internationally agreed way in which we describe the flow of current in all circuits that we set up. Okay, let's go back to our simulation. So by convention, the direction of current is taken to be from positive terminal to the negative terminal, as we have demonstrated that. Right, okay, so this is what we meant in as far as the conventional current. So that's our positive to negative. So that's our positive terminal to negative terminal. All right, okay, questions now. Let's consider a simple circuit once again. We have set up a circuit like this, but using the real, devices. Now we can transform that to symbolic representation. We'll get something like this for an open, circuit. Here is a circuit. There are two cells that are connected in series. Okay, the switch is open. Okay, there are conducting wires. Then there are two ammeters connected at different points, and then there is a light bulb. Okay, so for us to interpret this, we need to understand the meaning of each of these symbols. Okay, now let's think about the following questions. What is the reading on the ammeter? Once the question says what, take note of that language, pay careful attention to it. The moment the question says what, it's either we know or we don't. We don't need to go via a way of calculations for us to arrive at the correct answer. So what, and it tests your knowledge, your remembering. Okay, now this is typically an open circuit, because it's a broken circuit rather, because the switch is open. Are there any charges flowing? If not, what is the current? So that's the thinking that we want to apply. So if the case is it's like this, we can go back to that simulation quickly, right? Let me take out the convention, right? Let's break the circuit by opening the switch. What is the corresponding reading on current? 0. You can even show the charges. Is there any flow of charge there? Definitely not. Okay, there's no flow of charge there. Okay. Okay. So because the charges are stationary, they're static. So hence there is 0 current, because there is no flow of current. Okay. So what does this tell us? That once the circuit is broken, it simply means that there is 0 current. Okay. The current reading will be 0 amperes. Okay. Ammeter reading rather. Okay. Right. Now we close the switch. Okay. The moment we close the switch, then there will be a reading on the ammeter. Okay. But now let's also recall that this is the positive terminal and that's the negative. While again on the ammeter, that's the positive end connected to the negative end. Similarly, this is what happens with the light bulb and as well as the what? As the ammeter, because we know that by convention the current flows from the current is from positive to negative, or charges move from positive to negative. So that's convention. Okay. So that we're talking about conventional flow. Okay, take note of that. So the assumption is always that we talk of the conventional. Right. Now, show the direction of current, indicate the positive and the negative terminal. So we would refer back to the source, which is the battery. That's our positive, that's our negative. So that's the direction of conventional flow. So on the ammeter, that's what we have. We have already demonstrated that from the positive to the negative of the battery. Okay, right. So that's straightforward. Now questions that involve, calculations. We are told that 48 coulombs of charge flows through a battery in 2.5 minutes, right? Take note of that time, all right? And we talk of a unit time. Does that suggest something? Yes, there are necessary conversions that have to be carried out in case we want to do some calculations of some sort, okay? It says here, what amount of charge passes through the light bulb in this time? Okay, what do we know? What do we know? We want the amount of charge here. What do we know? We know that current is equals to charge over time, okay? So what are we given here? We are given the amount of charge, okay, and the time. Now we want to calculate the ammeter reading, right? So the ammeter reading is the current. It will give us the indication of current, okay? How much charge is that? 48 coulombs, right? Divided by how much time is 2.5 minutes? okay, remember the SI unit of time is the second. So this will be 2,5 or 2.5 multiplied by 60. Why? Because for every minute there are 60 seconds, okay? So our current, if we quickly go to our calculator, okay, what does that give us? We have, let's clear that. The calculation is 48 coulombs into 2.5, okay, multiplied by 60, okay. So what does that give us? It gives us 8/25 as a decimal fraction, 0,32, okay. So the 0,32 is actually the ammeter reading, which is an indication of current strength, okay, 0,32 amperes, right? So be mindful of the fact that whenever you do calculations, make sure that the final value that you are calculating carries the correct unit. We are given the charge in coulombs. We managed to do the necessary conversion from 2.5 minutes to seconds, okay? And then whatever we're looking for in this case, which is the ammeter reading, which is an indication of current intensity or strength of current, or simply put, the amount of current that passes through a point, you know, then we managed to get to that, okay? Then if we can go back, the amount of charge that passes through the light bulb in this time is exactly the 48 coulombs. That's the amount of charge, okay? Right. And then in summary, we understand that current is the rate of flow of charge. This is an all or nothing type of a definition. And then an ammeter is a device, that's an instrument. Current is a quantity, all right? Let's make sure that we understand that. And then ammeter is a device that is used to measure this quantity that we call current. Okay, it is always connected in series or at a point. Okay, the thinking about that was that it actually, we want to establish the amount of charge that passes through a point per unit time. And then we say that, you know, an ampere of current is actually equals to 1 coulomb of charge passing through a point per second. So when we had an ammeter reading of 3 amperes, equivalently what we are saying there's 3 coulombs of charge that pass through a point for every second. So this is the long and short of, you know, what it exactly means when we talk about current. So in as far as the big ideas that have got to do with electricity, what do we know now? We know a lot about current, how to measure current. We can also, by now, measure voltage, you know, either of the battery, okay, which is in terms of the EMF and the potential, the terminal potential difference. But our focus today was on understanding the concept of current. Right, so that's as far as, you know, exploring current is concerned. You know, some of the things that are also very important and worth mentioning is that in the calculations that you carry out involving the equation I is equals to Q over delta T, make sure that you copy the formula as it is given. You know, even if we were looking for charge, you'll write the formula as it is given in the data sheet. I is equals to Q over delta T. Do the necessary substitution, but be mindful of the fact that there may be cases where you have to necessarily conduct some, you know, conversions to SI unit, because everything is about SI units. And then what follows after that is obviously the maths, okay? Now, that's the time that we have for today in as far as exploring current. Hopefully it made a lot of sense to you. From myself, it's cheers and bye-bye for now.